Saturn's rings are the single most photographed structure beyond Earth. Every telescope, every postcard, every science textbook cover seems to agree on one thing. This is what a planet is supposed to look like. For most of the last 300 years, astronomers assumed those rings were as old as Saturn itself, a leftover halo from the birth of the solar system, frozen in place for 4.5 billion years. That assumption is now dead. As of today, July 24th, 2026, the picture has changed completely. Data from the Cassini spacecraft, combined with a set of remarkable new simulations published earlier this year, suggest that Saturn's rings are not ancient monuments at all. They are the wreckage of a catastrophe, a chain reaction of collisions, resonances, and gravitational chaos that started with a moon that no longer exists and ended with the solar system's most beautiful accessory, and the moon at the center of the whole disaster turns out to be one we can still see today, Titan. This is the story of how scientists finally worked out where Saturn's rings came from, and why the answer forced them to rewrite the history of an entire moon system, a 400-year-old puzzle. To understand how strange this discovery really is, it helps to go back to the very first person who ever looked at Saturn through a telescope. In 1610, Galileo Galilei pointed his primitive spyglass at the planet and saw something that made no sense to him. Saturn didn't look round. It looked like it had two large companions pressed against either side of it, almost like handles on a jug. Galileo had no name for what he was seeing and no way to resolve it further. 2 years later, when he looked again, the handles had vanished entirely, only to reappear a couple of years after that. We now know exactly what confused him. Saturn's rings are tilted about 27 degrees relative to its orbit. As the planet travels around the sun, that tilt means the rings appear to open up toward Earth for a while, then gradually close until we're looking at them edge on. At which point, a structure that spans hundreds of thousands of kilometers becomes almost invisible because it's only a few dozen meters thick. Galileo wasn't watching the rings disappear. He was watching them turn sideways. It took roughly 50 years of improving optics before anyone figured out what was actually going on. In 1659, the Dutch astronomer Christian Huygens proposed that Saturn was surrounded by a thin, flat ring, unattached to the planet's surface. Huygens is also credited as the first person to spot Titan, which makes him an unusually important figure in this story before the story has even really started. A few decades later, the Italian-French astronomer Giovanni Domenico Cassini, after whom the later spacecraft would be named, discovered 4 more of Saturn's major moons, Iapetus, Rhea, Tethys, and Dione. In 1675, he also spotted a dark gap running through the rings, a division that still carries his name today, the Cassini division. The next real leap came in the late 19th century when astronomer James Keeler demonstrated that the rings couldn't possibly be solid sheets of material. If they were, the outer edge would have to spin slower than the inner edge, and the physics simply didn't hold together. Keeler showed that the rings were actually made of countless individual particles, each one independently orbiting Saturn like a tiny moon of its own. But it wasn't until the space age that anyone really understood the scale and intricacy of what they were looking at. The Pioneer and Voyager probes of the 1970s and early 1980s each added more resolution, more detail, more unanswered questions. And when Voyager 2 flew past in 1981, it revealed that the broad rings originally labeled A, B, and C were themselves, built from thousands of narrower ringlets, nested inside one another like grooves on a record. Then came Cassini, a mission that spent 13 years in orbit around Saturn, threading itself through gaps in the rings, skimming past moons, and finally, in its last months, diving repeatedly through the narrow space between the planet's cloud tops and its innermost ring before burning up in the atmosphere, on purpose. The data that mission sent home didn't just refine our picture of Saturn, it broke it and then rebuilt it into something nobody expected. What Cassini actually found Saturn's rings, it turns out, are almost absurdly thin, across a system that stretches out to roughly 282,000 kilometers from the planet. The vertical thickness in most places is somewhere between 10 meters and 1 kilometer. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper wrapped around it. Officially, the rings are named in the order they were discovered, rather than the order they appear physically from the planet outward, which is why the sequence looks a little odd: D, C, B, A, F, G, and E. There's also a final, extremely faint and distant structure, called the Phoebe ring, tucked far out along the orbit of the moon it's named after. Holding those particles in their lanes is a small fleet of what astronomers call shepherd moons. Pan, Daphnis, and Prometheus sit inside the main ring structure itself, nudging particles back into place through their gravity. Pandora, Janus, and Epimetheus orbit just beyond the outer F ring, performing a similar job. Farther out still, the moon Mimas, discovered by William Herschel back in 1789, exerts an outsized gravitational influence on the whole system despite its relatively small size. Chemically, Cassini confirmed that the rings are almost pure water ice, about 99.8%, with individual particles ranging from grains smaller than sand up to chunks the size of a house or larger. It's that ice that makes the rings so reflective, bright enough to see from Earth, with equipment no more sophisticated than what Galileo had 4 centuries ago. Here's where the story gets interesting. Cassini also allowed scientists to calculate the total mass of the ring system, somewhere around 16 quadrillion tons. That sounds enormous, and it is, but it's still less than 0.02% of the mass of Earth's own moon. The rings, in other words, are surprisingly lightweight for something so visually dominant. Combine that light mass with the ring's brightness, and you get a genuine scientific contradiction. Over time, space is constantly raining micrometeorite dust onto everything in it. That dust darkens exposed ice, the same way dust darkens a windshield. Scientists could calculate how much dust it would take to noticeably darken a ring system of that particular mass, and the number came out surprisingly small, which meant that, rings should have looked dirty and gray long ago, if they'd really been sitting there since the birth of the solar system. They don't look dirty, they look bright and clean. The only way to reconcile that observation with the physics of dust accumulation was to conclude that the rings are young, probably somewhere between 10 and 100 million years old. In the 4.6 billion year history of the solar system, that's a rounding error. It means Saturn's rings formed at roughly the same time dinosaurs were already well established on Earth, not during the planet's formation. That single realization turned a settled question into an open one. If the rings didn't form with Saturn, something must have created them much, much later. The obvious next question was, what? The Roche limit and the first real theory, the person who laid the groundwork for answering that question, wasn't working with spacecraft data at all. He was working with pen, paper, and Newtonian mechanics in the year 1849. French astronomer Edouard Roche was trying to figure out a specific pattern. Why do rings only ever show up around the giant planets, and never around smaller rocky worlds like Earth or Mars? Roche's answer involved tidal forces. The same kind of pull that causes ocean tides here on Earth, just scaled up dramatically. A planet's gravity doesn't pull on every part of an orbiting moon equally. The near side gets tugged harder than the far side. Push a moon close enough to a large enough planet, and that difference in pull becomes strong enough to overpower the moon's own gravity, the force that's holding it together as a single object. At that point, the moon doesn't just get perturbed, it gets torn apart, and the debris spreads out along the orbit it used to occupy, eventually flattening into a ring. Roche calculated roughly where that breaking point would sit for any given planet, about 2.5 times the planet's own radius, measured from its center. For Saturn, that works out to approximately 87,000 kilometers, though distance that, notably, lines up closely with the location of the outer F ring. Roche's mathematics gave scientists the mechanism. What it didn't give them was a victim, an actual moon that could plausibly have wandered into that danger zone and been destroyed. That's the piece of the puzzle that spacecraft data would eventually help fill in more than 150 years later. Chrysalis, the first modern candidate. By 2022, with the age of the rings firmly established by Cassini's measurements, a team of researchers at MIT proposed a specific culprit. They suggested that an additional moon had once orbited Saturn somewhere between Titan and Iapetus. They gave it a fittingly dramatic name, Chrysalis. According to their model, Chrysalis had its orbit gradually disturbed by the gravity of Titan over a very long stretch of time. Eventually, that disturbance pushed Chrysalis too close to Saturn, straight into the zone Roche had described more than a century and a half earlier. Torn apart by tidal forces, its remains spread out and eventually settled into the ring system we see today. It was an elegant story, and for a while it was the leading explanation. The name itself was even meant to be poetic. Chrysalis, the case a caterpillar breaks out of, transformed into something else entirely. In this case, into rings. But an elegant story isn't the same thing as a correct one, and elegance doesn't survive contact with more detailed simulation. That's exactly what happened next. The problem with Chrysalis. In February 2026, a team led by astrophysicist Mattia Chuk at the SETI Institute, working alongside researchers from the Southwest Research Institute, Caltech, and the Observatoire de Paris, ran the Chrysalis scenario. Through far more detailed numerical simulations than had been attempted before, their conclusion was blunt. In the vast majority of outcomes, Chrysalis wouldn't have made it to Saturn at all. Long before it could get anywhere near the Roche limit, its unstable orbit to home would have brought it into the path of something much closer and much larger, Titan itself. And when a mid-sized moon crosses paths with a body the size of Titan, the far more likely outcome isn't a graceful slingshot toward the planet. It's a direct collision. If that collision happened, the physics changes completely. Most of the wreckage from a moon smashing into Titan would either be absorbed by Titan's own gravity or ejected from the Saturn system altogether, flung out into space and lost. Neither outcome produces a ring. There was a second problem, and this one turned out to be the more important clue. In nearly every simulation where the extra moon was destabilized, the small moon Hyperion, misshapen, chaotically tumbling, and locked in a resonant relationship with Titan, was thrown out of the system entirely along with it. That's a problem, because Hyperion is still there. We can see it. Cassini photographed its bizarre, sponge-like surface up close in 2005, and it remains locked in a stable 4-3 orbital resonance with Titan to this day. For Chuck, that contradiction became the key to the entire mystery. If Hyperion so rarely survives the chrysalis scenario, but Hyperion clearly did survive, or more precisely exists right now, then maybe the story had the wrong shape. Maybe Hyperion wasn't an accidental survivor of some earlier catastrophe. Maybe Hyperion was a product of it, Proto-Hyperion, and the real collision. Working from that insight, Chuck's team widened their approach. Instead of modeling one moon in isolation, they modeled the entire Saturnian satellite system as an interconnected whole, accounting for Saturn's unusual 27-degree axial tilt, the current orbits of its major moons, and the timing evidence buried in Hyperion's resonance with Titan. What emerged from running dozens of these simulations was a new candidate for the vanished moon. Not chrysalis, but something the team called Proto-Hyperion, a body roughly 4 times more massive than chrysalis had been proposed to be. The name was deliberate. In this scenario, the moon we know as Hyperion today isn't a survivor from before the disaster. It's built from the leftovers of it. At the time all this happened, Titan itself looked different too. Smaller than it is now, and sitting in a more circular orbit than the elongated path it follows today. Across 60 separate simulation runs, a direct collision between Proto-Titan and Proto-Hyperion occurred in 42 of them. In the runs where no collision happened, the alternative outcome was almost as dramatic. Either Proto-Hyperion or the outer moon Iapetus got flung out of the Saturn system entirely. The team dates this event to roughly 400 million years ago, and they argue that it set off a chain reaction that can explain an unusually long list of things astronomers have puzzled over for years. Titan's atmosphere, its youthful surface, its rapidly expanding orbit, Saturn's own tilt, Iapetus's strange inclination, and eventually the rings themselves. So how did one collision cause all of that? It starts, oddly enough, with something happening to Saturn itself, not to any of its moons. Resonance. The chain reaction begins. To follow the rest of this story, you need to understand resonance because almost every step from here forward depends on it. Orbital resonance happens when two bodies orbit in a repeating, synchronized rhythm, meeting up in the same relative positions again and again. Each time they meet, a small gravitational tug passes between them. On its own, one of those tugs is negligible, but repeated over millions of orbits, those tiny nudges accumulate, reinforcing each other until they produce genuinely large-scale changes in how the bodies move. According to the SETI team's model, the whole cataclysm began when Saturn slipped out of an older, long-standing spin-orbit resonance it had shared with the other giant planets. That single shift was enough to destabilize Proto-Hyperion, knocking it into a 2-to-1 resonance with Proto-Titan, the strongest and most disruptive kind of resonance there is. In a 2-to-1 resonance, one body completes 2 orbits for every single orbit the other body completes. In this case, that meant Proto-Hyperion orbiting Saturn twice for every 1 lap that Proto-Titan made. The repeated gravitational tugging from that relationship rapidly dragged Proto-Hyperion's orbit inward, sending it on a collision course with Proto-Titan, and in the process, yanking on the orbit of Iapetus as well, tilting it into the unusually inclined orbit we still observe today. Eventually, Proto-Hyperion and Proto-Titan's paths crossed and the two bodies collided. Why Saturn itself? Tips over. Here's where the story stops, being just about moons, and starts explaining something about the planet itself. Resonances in a system like this aren't limited to linking one orbit to another. They can also link the orbit of a moon to the spin behavior of its host planet. No planet is a perfectly smooth sphere. The combined gravitational influence of the Sun and its moons flattens gas giants into what's called an oblate spheroid shape. That imperfect shape causes the planet to wobble slightly as it spins in a process called precession, similar to the way a spinning top wobbles as it slows down. As Titan's orbit rapidly expanded following the collision, it altered the rate of Saturn's precession, causing the planet to wobble faster and faster. Eventually, that accelerating wobble pushed Saturn's axial spin into a resonance with the orbit of Neptune. The only way for that particular lock to be sustained, as Titan kept drifting further outward, was for Saturn's rotational axis to tilt. Under normal planetary formation processes, giant planets are expected to end up with close to zero axial tilt. Saturn's actual 27-degree tilt has puzzled scientists for a long time as a result. The scenario proposed by Chuck's team is currently one of the most convincing explanations put forward for that anomaly, tying Saturn's signature sideways lean directly back to the same collision that reshaped Titan and created Hyperion. Stage 2. Building the rings. After the initial collision, the Saturnian system settled into a period of relative calm, roughly 200 million years according to the model. But Titan's slow, steady outward drift never stopped, and it eventually triggered a second wave of destruction. About 100 million years ago, Titan's orbit locked into a 4-to-1 resonance with a pair of inner moons, likely Protodion and Protorhea, based on the team's simulations. That resonance tilted Titan's orbit further and dramatically shifted the orbits of those two inner moons, eventually driving them into each other. The resulting collision, combined with the tidal stress of Saturn's own gravity, pulling at close range, tore both inner moons apart. Some of that debris eventually reaccreted into new, smaller moons. Some of it was lost to space entirely, and the rest spread out into the thin, flat, orbiting disk of ice particles we now recognize as Saturn's rings. That's the full sequence. A spin-orbit resonance breaking loose, triggering a collision between Proto-Titan and Proto-Hyperion, which reshaped Titan, tilted Saturn, and set Titan drifting outward fast enough to eventually destabilize the inner moon system, producing a second collision that finally created the rings we see today. It's a genuinely elegant chain reaction in the sense that every step causes the next one. And it means the rings aren't a separate event from Titan's strange orbit, or Hyperion's strange shape, or Saturn's strange tilt. They're all outcomes of the exact same underlying disaster, just playing out on different timescales in different parts of the system, tying it all together. Step back and look at the full list of previously unconnected mysteries this single model accounts for: the unusual tilt of Iaptis's orbit, the improbable age and shape of Hyperion, Titan's thick nitrogen atmosphere and unexpectedly young surface, Titan's rapidly expanding elliptical orbit, Saturn's own 27-degree axial tilt, and finally, the youthful, bright rings themselves. None of those observations are new. Scientists have known about most of them for decades. What's new is the recognition that they're not a pile of separate coincidences. They're a single continuous story, and Titan sits at the center of all of it. That's what makes this particular piece of research stand out. None of the underlying physics involved, orbital resonance, tidal forces, planetary precession, is novel. Every one of those concepts has been understood and taught for a long time. What Chuck and his colleagues did differently was refuse to treat each anomaly as its own isolated puzzle. By modeling the entire system together, they found a way to connect observations that nobody had previously thought belonged in the same conversation. Putting the theory to the test. A model this ambitious naturally invites scrutiny, and scientists outside the SETI team have generally responded with cautious enthusiasm rather than outright acceptance. Several planetary scientists who reviewed the paper after its publication in the Planetary Science Journal in February 2026 have described it as a substantial improvement over the earlier chrysalis hypothesis, largely because it doesn't require an implausibly low probability sequence of events to work. Experts who were part of the original Cassini science team have also noted that the scenario offers a coherent explanation for a wider set of observations than any previous model. Still, convincing isn't the same as confirmed. The strongest possible confirmation would come from direct physical evidence on Titan's surface itself, something that isn't available yet because Titan is too far away and too shrouded in haze for existing telescopes or the retired Cassini spacecraft to examine in the kind of detail this theory would need. That's where NASA's Dragonfly mission comes in. Dragonfly is a nuclear-powered, car-sized rotorcraft designed to fly from location to location across Titan's surface, collecting and analyzing samples as it goes. It's currently scheduled to launch in 2028 and is expected to arrive at Titan in the mid-2030s. Once there, its instruments will be capable of examining Titan's surface chemistry and geology in a level of detail no previous mission has managed. If Titan really was reshaped by a massive collision a few 100 million years ago, Dragonfly may be able to find geological signatures, buried impact features, unusual surface chemistry, or resurfacing patterns that would provide the kind of direct evidence this theory currently lacks. Chuck and his co-authors were careful to frame their own conclusions modestly. Even if the exact sequence of events they describe turns out not to hold up under future scrutiny, they argue that the broader approach, treating the whole satellite system as a single connected dynamical puzzle rather than a set of isolated mysteries, gives future researchers a valuable new framework for generating hypotheses about how Saturn's moons evolved. A ring system on borrowed time. There's one more piece of this story worth knowing, and it's a strange kind of cosmic irony. Saturn's rings, having formed only in roughly the last 100 million years, are not going to last much longer either. During Cassini's final orbits in 2017, the spacecraft repeatedly dove through the narrow gap between Saturn's cloud tops and its innermost ring before deliberately plunging into the planet's atmosphere. Those close passes revealed that the rings are actively raining material down onto Saturn, up to roughly 40 tons of ice particles falling into the planet's atmosphere every single second. At that rate, scientists estimate the rings have, at most, a few 100 million more years before they effectively disappear. Put those two numbers together and the picture that emerges is almost unsettling. Saturn's rings existed for a negligible sliver of the solar system's history before we were around to see them, and they'll be gone again for a negligible sliver of time after we're not. Researchers studying the Saturnian system have taken to describing it as a dynamicist's paradise, a system so interconnected and so actively evolving that its current state is really just a brief snapshot of an ongoing chaotic process. We happen to arrive at almost exactly the right moment in that process to see the rings at their most spectacular. A few 100 million years earlier, they wouldn't have existed yet. A few 100 million years from now, they'll likely be gone. So, as of today, July 24th, 2026, this is where the science actually stands. Saturn's rings are not primordial. They are the byproduct of a violent multi-stage collision event that began roughly 400 million years ago, when a moon we now call Proto-Hyperion collided with a smaller, younger version of Titan. That single event reshaped Titan's surface and atmosphere, tilted Iapetus, sent Titan drifting outward at an accelerated rate, tipped Saturn itself onto its side, and eventually triggered a second collision between two inner moons, whose wreckage spread out into the thin, icy disk we now call the rings. It's a theory built from decades of patient observation, a genuinely creative piece of modeling work, and one very stubborn contradiction involving a small, tumbling, oddly shaped moon that simply refused to have disappeared when the old theory said it should have. Whether the details hold up exactly as proposed will likely depend on what NASA's Dragonfly mission finds when it finally reaches Titan's surface in the next decade. Until then, the rings remain what they've always been, the most visually stunning structure in the solar system, and we now know, one of the youngest. It's worth sitting with how quickly this understanding has shifted. For the better part of 4 centuries, the rings were treated as a fixed, unchanging backdrop, something Saturn was simply born with, a permanent decoration rather than an active, evolving system. It took a spacecraft, spending over a decade in orbit, a team willing to model the entire moon system as one interconnected machine rather than a collection of separate objects, and one small, oddly shaped moon that stubbornly refused to fit the old story to finally crack it open. That's often how the biggest shifts in planetary science actually happen. Not through a single dramatic image or a single blinding piece of evidence, but through a slow accumulation of small inconsistencies, a ring system too bright for its age, a moon drifting outward too fast, a tilt with no clean explanation, a tiny tumbling satellite that shouldn't have survived the story scientists were telling about it. Individually, none of those anomalies were dramatic enough to overturn a settled theory. Together, modeled as one connected system, they told a completely different story than anyone expected. Saturn has been a fixture of the night sky since long before telescopes existed, and it will remain one for a very long time to come. But the version of Saturn we're looking at right now, rings and all, is a temporary one, a few 100 million year window in a 4.5 billion year history, framed on one side by a moon-shattering collision, and on the other by an ending that's already quietly underway. We just happen to be here to see it.